Hello, I'm Loren Pfeiffer. I have been at Princeton for about 11 years, but I've spent my entire career in materials science, the physics of materials, and in particular the physics of gallium arsenide and aluminum arsenide and gallium aluminum arsenide electronic materials.
Loren Pfeiffer, Ken West, and Kirk Baldwin were a team who used to work at Bell Labs. They were responsible for growing the highest quality material even back then, in the 80s, 90s. They have records of this dating all the way back to 1987 in the lab.
I'm very excited because in the last year we made tremendous progress. Consider the fact that I've been working in this field since 1987 and we had a standard that we were growing. I've been trying to make this material as a function of density, and this is essentially mobility or quality of the gallium arsenide quantum wells, have been getting better and better, but they've been sort of stuck at this red line as the best we could do for essentially since about the year 2000. May of 2019, we got a hint of this. We violated the line in the upside. We were very excited about it. And since then, we learned what to do, and we've grown things. We've grown a whole series of these runs that's parallel to the red line, but a factor of 2 higher. So with this as a background, I want to give you a tour of the laboratory and how we in fact made this accomplishment.
My name is Edwin Yunjang Chung. I'm a 6th-year graduate student. My dissertation research is to grow the highest quality gallium arsenide and aluminum arsenide samples in the world. We have made significant progress. Now the aluminum arsenide samples are more than a factor of 6 better than they had been previously, and for gallium arsenide they're enhanced by a factor of 2. Such improvement was considered to be impossible or very difficult, but Loren has a very talented group of people here, and I was part of that team.
So this is the MBE machine that we built here at Princeton. We started building this machine in 2011, 12, and designing it, and then putting it together in 2013 and 14. By 2015 it was done, but it took another 2 or 3 years to learn how to run the new machine. Over here is the guts of the machine, and it's called the growth chamber. In the growth chamber, there's liquid nitrogen surrounding the growth environment. The sample is here, right there, and these are interesting, these cells. These are arsenic cells, aluminum cells, and gallium cells, and they're heated to allow molten material to vaporize and land on the substrate. And that's controlled with shutters which operate and block the path or not block it as we choose. This part of the machine is the load lock. We use these rods which allow us to move samples in and out of the machine. As we load it into this chamber, the loading chamber, with this rod, move it over through this valve and this valve to a wheel here, and then we use a second rod to move the sample from here all the way into the machine and out again. So we can actually transfer samples into the machine and out of the machine without ever breaking any vacuum. These are the pumps for the load lock area, and the key feature that's new here is we put a special 10 kilowatt pump that actually has a cold finger right in the growth chamber, and that has made a huge difference in the quality of our latest material. This machine is actually growing material right now, and if you look up here you can see this little rod connects to gears inside the machine which lets the sample rotate. Well, you've seen my laboratory, at least a small bit of it. We can show in a few minutes, and thank you for your attention.